I'm sorry I can't use my video because my webcam is broken. So, but hopefully the sound is all right. Okay. So the introduction to modular form. So the definition first, let H denote the upper half plane of the complex. In essence, is the set of all Z in C such that the imaginary part is positive. And then let C infinity denote C union infinity. Also, let SL to R denote the graph of matrix ABCD such that ABCD is an element of real and AB minus BC is 1. So basically, the determinant is 1. Now, we have an action on of SL to R like this. Given G is a matrix ABCD in SL to R and Z an element of complex infinity, we define GZ as AZ plus B per TZ plus B, while G infinity is A per C, or the limit of Z to infinity of GZ. Correspondingly, J of minus B per C is infinity, and if C is 0, then G infinity is infinity. So, this action is very important in modular group. So to understand it better, let's try to do the exercise 1. Check that G is a group action on C infinity. So in essence, let's try to prove that G1 composed with G2Z is equal to G1 times G2 as a matrix. So the G1 and G2, we first multiply them as a matrix and then use the result of the multiplication as a function of that. So maybe I'll use this whiteboard here to annotate. So first, let G1 and G2 element of SLC R where G1 is A1, B1, 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 and B2 is A2, B2, B2, B2. So if we multiply this matrix, we have B1 times B2 is A1, A2, as B1, B2, B1, A2, plus B1, B2, A1, B2, plus B1, B2, B1, B2, plus B1, B2. Okay. On the other hand, if we use this matrix as a function like the one we defined before, we have that G2Z is equal to, I'm sorry, there is two cases here. So before, if we have Z is equal to infinity, then G2Z is A2 per G2, while G1, G2Z will be G1 of A2 per G2. This means that this will be A1, A2 per G2 plus G1 plus G1 times A2 per G2 plus G1, which we can then transform into this A1, A2 plus G1, G2 per G1, A2 plus G1, G2. We can see that this is G1, G2, Z for Z infinity. So this for this. So we have this, the case when Z is infinity is true. So since I have a limited space here, if anybody want to screenshot my scribble in here, I will give some time, maybe about 10 seconds every time my whiteboard is full to let somebody screenshot it, or maybe they can wait because this meeting is recorded. So I'll give a bit of a time to screenshot this image. Okay, then now what happens if Z is not infinity? So if Z is not infinity, we have that G2 Z is A2Z plus B2 for B2Z plus B2. So using this in G1 or G1 B2Z, it will be a little bit messy, but we will have A1, we have enough space here. We will have A1 times this plus B1, then we will have this. This form can be simplified into this. which we can see once again that this is uh, uh, this is uh, true, that this will be the same with V1 times V2, which means that this is equal to V1 times V2 of so we have proof that V1 composite with V2Z is equal to V1 times V2 of so quite an interesting function here. So basically, we can preserve the multiplication of matrix. Okay, I think this is enough. So let's go back to the so we have exercise 2, but this one is fairly easy, so I will have it as an exercise. You can show that plus minus identity matrix are the only element of SLR that acts trivially on the complex infinity. And then exercise 3, we can show that the image of Vz is equal to Vz plus V absolute value, the norm here. So basically, just uh, that uh, we can show that this is. I also think this one can be left as an exercise. It's not very hard to improve. Now, now we define that SL2 that is the subgroup of SL2R with integer and unit. This is obvious. Then gamma is SL2Z without plus minus identity. This gamma is called the modular group. Okay. Okay, so we have fundamental domain here. I will not explain it to detail because it's very long. But basically, if G is a subgroup of gamma, we say 2 points Z1 and Z2 in H. Remember, H is the upper half of complex plane. So basically, this H is this one. We say that 2 points Z1 and Z2 on H are G equivalent if there exists a matrix G such that G Z1 is equal to Z2. So basically, if we can find a matrix that makes it so that if G is equal to A, B, C, D, or we can find A, B, C, D such that AZ1 plus B plus AZ1 plus B is equal to Z2. something like that. Then Z1 and Z2 is G equivalent. A closed region F in H is called a fundamental domain for G if for every Z in H is G equivalent to a point in F, but no two distinct points in the interior of F are G equivalent. So then we can compute that the theorem 1, the fundamental domain for gamma is in here. So basically in the area where the real part of Z is between minus a half and half, and the norm is more than 1, so outside the circle. So basically what it means is that for any point in the upper plane of complex, so if we have it here, maybe we can find a G such that when we calculate GZ1, then the result will be somewhere inside this domain. On the other hand, for any 2 points in this fundamental domain, so if this is Z1 and this is Z2, we can find any G such that Z1 is equal to Z2, something. Okay. So now we define these two metrics that are pretty important. S is equal to 0 minus 1, 1, 0, and T is equal to 1, 1, 0, 1. So why is these two metrics important? We'll see. Now this corollary too. We can prove that gamma, so gamma is this, right? L Z without plus minus B, will be generated by F and T. Okay. So maybe I will try to prove it. There is a proof here which use uh, complex analysis, but I will try to give alternative proof here. So let's see. So gamma. Okay. So we have gamma is equal to yeah. We will try to prove that gamma here is generated by S and D on multiplication. So the idea here is we would prove that for any matrix A, element gamma, we can write it as this. We can always write it as the multiplication of P and X. So the idea here, is that first uh, we see that S squared 0 minus 1 by 0 squared is 0 and 0 1. So this um, minus 1 0 0 minus 1, it is uh, minus identity. Probably. So I think there is something. Yeah, it should be identity. Okay, sorry. So yeah, this is minus e. But if we look at the function that we have defined, we know that minus e of z is minus z plus 0 per 0 plus minus 1, which is the same as z plus 0 per 1 plus 0 plus 1, which is the same as I z. So basically, minus e and e in the function is the same. So which means that in this multiplication, that s squared is not is trivial, because if we pair two s together, it will disappear. Which means that if s appear in this multiplication, they will only have the power of one. Mhm. Now, so another note, the inverse of s is 0, 1, minus 1, 0. The inverse of t is 1 minus 1, 0, 1. So the idea here is, for example, let's take A is equal to any random matrix that have determinant ones. Let's let's say maybe 4, 25. So we also can calculate that p to the power of n will be like 1 n 0 1. So if we have a like this, then we can have some value f n such that so the the first column is the same, but the second column will be change. We can find some n such that value is less than 11. Right? For example, we take n equal to -3, then it becomes 3, which means that if we have a times p minus n, so that's n is -2, right? So AP to the power of -2 will be for 11, then this is 3, and the upper one is 1. So we have reduced the value quite a bit on the second column. I have to do it sometime if you want to screenshot it. Okay. So basically what we have here that we can always find n such that n if this one is a b c d, then uh, the none of these is less than none of these. So the idea is this. Wait, this is because as you can see, we can find it n such that c become larger than c. Now, if we multiply this with n, what we have is that will become -1 4 -3 0. Oh, wait. Oh, no. This is, I'm sorry. This is S inverse. No, S is this. Sorry, I used the wrong. So this is 1 -4 3. So we can see again that we have what we have we exchange the first column become the second column, and the second column become the first column, but the second column is multiplied by -1. So again, we can find some n. We can then multiply this again with some p to the power of n, right? So this should be 1 3 -4 1 n will become 1 and 3 1 and 4 3 11. Okay. Now we can find again some n such that the absolute value of c is bigger than this. So we can see that this is 3 and this is 11, right? The absolute value. This is still bigger. So we need to find some n such that the value here will be bigger than this. So we can take n equal to 4. We will have a p minus 2 and p 4. Right, this is 1 0 3 and 1. So now this one, the absolute value is bigger than absolute value of 1. Okay, and then if we multiply it again by s, we will have 1, 0, minus 1, minus 3, because we will exchange the column. The first become the second, second become the 1, and then the second column will be multiplied by negative 1, right? And we do this again. All right. So basically what we do here is that every time we multiply this with c to the power of something such that the absolute value of c is bigger than d, and then we multiply it by s, then we exchange it again so that the c will become smaller again than d, right? Then we multiply it again with some n, t to the power of n. So something like this, which will make it into 0, 1, and something, right? So we can find some n such that the absolute value of this one will be smaller than this. If we keep doing this, we will become smaller, smaller, and smaller. Eventually, we will reach 0, right? So in this case, since this is 1, the only way this can be smaller than 1 if this is 0. So this is actually like almost the final step here. So to make it brief, uh, I will use n equal to 3. We can multiply by 3 here, and then the result will be 1, 0, minus 1, 1, 0. As which we can see that this is s, right? So we have that I e minus 2 f equal f e3 is equal to s. And then we can just move this one here to have to get that a is s times c minus 3 times. Remember that we have shown at the beginning that s inverse and s is equivalent here. So 3 minus 1 s and d squared. So we have expressed a as the multiplication of s and t. This is just the idea. So I in this case I use a specific value of a, right? So then, but we can change the value of a into a generic ABCD. We can still use the same idea, right? I left that as an exercise. So this is just the idea on how to prove that gamma is generated by S and T over multiplication of matrix. Okay. Have some time to screenshot or write this down. Okay. So we have proved that gamma is can be generated by S and T. This is very important to to our next result. Go back here. So this is also quite interesting. We love this kind of exercise. So, okay. So we finally go into a modular function. So why are we talking about the set gamma and the fact that it is generated by S and T, right? So we define let k be an integer and fz be meromorphic on H. So suppose that fz satisfies this. So fz, so basically this is if this is G, right? So basically fgz is for any matrix in gamma. Since we have proved that gamma is generated by S and T, we can just check whether this is true for f x z and f e z. So basically, we can simplify the proving. So we can simplify how to check if a function is a modular function or not, something. Okay, so since S is S is F is this, right? F is 0 minus 1, 1 and 0. This means that SZ is minus 1 per Z. So this one. We just need to prove that F minus Z and minus 1 per Z here is equal to, so because C is 1 and D is 0, so this is the same as Z to the power of K times FZ. And then for T, since T is 1, 1, 0, 1, which means that Tz is Z plus 1 per 1, so plus 1. We must prove that F Z plus 1 here is, so because the C is 0 and D is 1, this will be 1 to the power of K, but 1 to the power of K is always 1, so this is the same as F squared. Basically, we just have to prove these two identity. If we can prove this two is correct, then obviously it will be correct for any ABCD on gamma. Okay. So now, if we have a function that satisfies these properties, if we express this function as sigma of an times qn, where q is this, a to the power of 2p iz, we can see that this will always satisfy these properties, right? Because fz1 was basically we just add the plus 1 here. But since 1 times 2pi will always cancel each other out, so we will always satisfy this one. Okay. Now we only have to satisfy this one. Okay, So further, if f is meromorphic at infinity or in Fn, at most finitely many non-zero an for n negative. So basically, so if this is an element set, right? So we have this from minus infinity, uh, minus 2 to minus 2 something, right? If this is meromorphic at infinity or at most finitely many non-zero an uh, for n negative, we have that there is a minimal value such that for any n smaller than n, it will be all zero. Or basically, uh, we can have it start from some point n. How to no, basically, uh, a modular function which is holomorphic everywhere is called a modular form. So basically, it is a modular function which starts at n equals 0. So for any n negative, the an is 0, which means we can start from n is equal to 0. Which satisfies this one. Okay, so as I have explained before, if we express the function in this form, then the fact that we take this will always mean that we satisfy this condition, which means the only condition left to consider is this. So basically, modular function is a function in this form, which satisfies this property that f minus 1 per z is equal to z to the power of k of x. If a0 is also 0, which means we can start from n equal 1, then we call this a cusp form. Okay. So now we define mk gamma as the set of all modular forms of weight k for gamma. Correspondingly, Sk gamma is defined to be the set of cusp forms of Vk for gamma. Obviously, Sk is a subset of Nk. So this is some example of modular function. This here is Ramanujan's theta function. This is a cusp form of weight graph and is defined like this. Which is interesting because we actually have an explicit formula for tau n, yeah, which is found by McDonald-Tyson. We call this a McDonald-Tyson formula. Okay. So now some remarks on modular function. If k is an odd integer, there are no non-zero modular functions of the k for gamma. So this is actually pretty easy, but maybe I will prove this one as an to further understand why is this. Yeah. So it- okay. Why? So suppose that f is a modular function. We may say so according to the definition that we have here, which this means that f minus 1 percent f to be equal to z to the power of k and z, right? But remember that modular function also have to satisfy this step for any g equals to a, b, c, d. We must satisfy that f is equal to z plus b. So this maybe this is too specific. We use the more general properties that they must satisfy this for any g, a, b, c, d. We must satisfy this one. So we hit e minus 1, 0, 0, minus 1. So we have to satisfy that. So the gz here is minus 1 times z plus 0 by 0 plus minus 1 is equal to minus 1 okay, after, which means that f that is equal to -1 to the power of k after. And out, since k is out, means that f that is equal to minus f that, which means that f that must be 0. So this is why we will never have a modular function with outlet. Now, this is quite an interesting property. So the set of modular functions form of the same weight forms a complex vector space under addition and scalar multiplication. We can then show that if f1 and f2 are modular functions of weights k1 and k2 respectively, then the product f1 f2 is a modular function of weight k1 plus k2. This is actually pretty important, but the slide doesn't mention this as its separate theorem, but this is very important. That if we have two modular functions, one with weight k and one with weight k2, if we multiply it, then it will form a modular function with weight k1 plus k2. So exercise 5, we can also, let's try to do this with exercise 5. So check if the transformation holds for G1 and G2, then it holds for the project G1, G2. Basically, this is the set. Let's do this. Actually, this uh, actually we should first prove this one uh, before we can So basically we have this before we have said that since uh, since gamma is generated by SNP, then we can just check this two. If this two is correct, then this is always true for any gamma. Uh, we actually have to prove these properties first, actually, yeah. So yeah, we work backward here, but it's okay. So that's good. So let's see one, one, two, one, 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 one. Right, itu is equal to itu, itu, and itu. Then one times itu is one itu plus one itu one itu plus one itu one itu plus one itu and one itu plus one itu. Okay. So since these properties hold for G1 and G2, which means we have like F G1 Z is equal to G1 Z plus G1 to the power of K, okay, and F G2 Z is equal to G2 Z plus G2 to the power of K times F. Okay. Also, we also know from the beginning that G1 compose G2 Z is the same as if we multiply the matrix first, right? Which means that F E1 times E2, okay, is equal to F E1 E2, okay, a lot of brackets here. And since we have this, if we use it on here, we get that E1 times E2 Z plus E1 to the power of K times F E2 Z. which means that now we use this. Here, we put the E1 and E3 plus E1 to the power of k times E2 plus E2 to the power of k times k. When if we compute this, we will have E1 times E3 with plus E1 times E2 and plus E3 to the power of k and k. So basically, since we want to prove that these properties hold for G1, G2, or basically this, then we need to prove that whether G1 is equal to this now. A bit complicated, but not very hard. Just a matter of calculation. Which will be hard. We just have to use the fact that G2 Z2 is okay. So we have that E1 times E2 that plus E1 times E2 that plus E2. This should be equal to E1 and G2Z is A2Z plus E2 plus E2Z plus E2 plus E1 times. As we can see, this and this is actually the same. So we can multiply them. This is just going to cancel each other to become C1 times A2 times Z plus C1 times C2 plus this one times this one becomes C1 C2 Z plus C1 C2. it can then be simplified into C1 into plus C1 C2 that plus C1 C2 plus C1 C2. So we have proved that this is the same one. So yeah, if we have proved this, then that's why when at first we define the modular function, we can simplify these properties into, you only need to check it for the matrix S and T, right? Because for any multiplication of two matrix, they always hold. Okay, so maybe you can screenshot or write this down for a minute. I'll take a break to drink some water. Okay, so let's go back to the net. Yeah, so let's review it a bit. Uh, why can we just check for SNP before? Because we have proven that exercise facts. Uh, Now we enter with Eisenstein series. So Eisenstein series are defined like this. So let k be an even integer greater than 2 for z in H. Define gkz is equal to sigma mn of 1 per mz plus n to the power of k, where mn is all integer, all pair of integer which is not both 0. Okay, so what makes this series special? So remember the definition of a modular function. It is they need to uh, satisfy these two conditions, right? F minus 1 per z is equal to z to the power of k times z and this one. So we now check whether this series that we have defined will it satisfy these two conditions? So let's see. Clearly, gk z plus 1 is equal to gk z. Why? Why is it clear? Okay. Since m is mn is a pair of all integer, then if we have z equal to 1, right? So basically, we have not space here. Okay, so basically, this is like this, right? So when we use mn in here, in gk, and the denominator is this line. So on gk z plus 1, wait, let me say that is gk z plus 1 is like this. 1 per, let's say we use an accent and an accent. So this is an times z plus an accent plus an accent k, right? So it seems to be different, but we just have to pick an accent. We just have to pick an accent equal to n, while an accent is equal to n minus an accent. If we substitute this back to here, we will get gk. This is the reason why gk z plus 1 is equal to gk z. So this one is satisfied. Now we check whether the other properties also satisfied. So for gk minus 1 per set, it is equal to this form, but you substitute z with minus 1 per set, obviously. We can then multiply the numerator and the numerator with z to the power of k. And this one, obviously, you might ask, well, but why is it dk? This is different, right? So this is mz plus n, this is minus n plus nz. So once again, we can just pick minus m. So maybe we can pick minus n is equal to an accent, while n is equal to an accent, right? So which means that this will become an accent that k per n accent that plus n accent to the power of k. So this one is more clear that this is the same, right? We use m accent and n accent, but m accent and n accent is also all pair of integer that is not but 0, which is gk. And since the numerator is zk, we can write it like this. So now we have proved that gk minus 1 per z is equal to z to the power of k times gkz, which means this property is also true. And since this means that GK satisfies the transformation for T and S, as we have talked about before, this means that GKZ is a modular function. Okay. This one. As we have proved before, because it satisfies the two conditions, then GK is an element of NK gamma, or basically GK is a modular form. It may be on the Okay, so we jump a bit here, but from the definition that GKZ is the sum of all these forms for all MZ, M and N integer, where not both zero, these actually have an explicit form of this. So for K even, oh no, sorry. For any K bigger than 2 and Z element of Z, and Z element of X, then G2K and Y2K, because the definitions of a, the definition is an even integer, right? So basically now we go for any K can be odd, but now this is 2K to make it sure it becomes even again. So G2KZ is equal to 2 times beta 2K times 1 minus 4K per G2K sigma, something like this. Where Q is this, the same as what we used at and the previous modular function. Sigma 2K minus 1n is the sum of all factor of n to the power 2K minus 1. So to give an example, sigma 3 of 6 maybe, and this is 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus 6 to the power of 3, something like this. And the Bernoulli number pk, which are defined by pk times x to the power of k per k factorial, the expansion of x per x minus 1. So how do we calculate Bernoulli number? Obviously, we can use the help of calculating software, but we can try to verify the first few Bernoulli number manually. So let's see here. Let's try to do the exercise 6. So we can now to the part is let's prove it. Okay. So how do you expand something like this? Well, we know that we can write it like this. And the expansion of exponential x is quite well known, right? It is like this. So 8 times 1 plus 8 plus x squared plus 3 factorial plus x cubed and so on minus 1, the power of minus 1, which then can be simplified into this. Maybe. Now, how do we calculate it? We can use the help of we can use the classic method, right? We want to divide x with this with one that one with and two and one. So we start from one. One times this is x plus plus two and with three and so on. X plus 6. And 4 and the more term you use, then you will be able to calculate more Bernoulli number. So, but right now I think this is enough. When we subtract it, we will have we can then see that for this to disappear, we need to multiply x by minus x per 2. Banyak x minus x per 2. That just going to do this again, and then until your limit. So how far can you do this? So either okay. So basically we will then can calculate that this is equal to this. The first few term is 1 minus x per 2 plus x squared plus 1 plus 0 minus x to the power of 4 plus this. So as you can see, this has no easy pattern to examine, right? So it seems random, which is why we need to have help from calculating software. But from this first 5 terms, we know that this should be b0 times, yeah, this is b0, this is b1 times x, this is b2 times x squared per 2 factorial, this is b3 times x cubed per 6, this is b4 times x to the power of 4 per 24. Which then, if you calculate it individually, b0 is 1, b1 is minus a half, b2 is minus 6, b3 is 0, and b4 is minus 1. And the more term you calculate, the more binary number you can find. So basically, this is for exercise. Okay. Maybe uh, you can take a screenshot or write it down. Uh, excuse me, I will need to take a little break to go to the bathroom. Please wait for me. Okay, thank you for waiting. Now let's go back to the Modular form. So as we can see and have proved before, Eisenstein series is a modular form, right? So G2K, this is a modular form with weight T, with weight 2K. So this is quite important, you know. And the fact that we have this explicit form means that we can expand it. Now, this theorem is just how you will be able to. So we have this, right? So theta 2K. Theta 2K is basically the sum of all reciprocal of n to the power of 2K. So how do we calculate this? This theorem has proved that it will be like this. So for the proof, I will not explain it here because it's pretty long and use it will be pretty hard to explain it online. But basically, this is the formula to calculate theta 2K. So what do we do with this information? So we then, this is just to verify what is theta 2 and what is the value of theta 4, we can just calculate it using the formula. So why is this important? So this form, this form of G2K here is ugly, right? The number is, as you can see, this contains P, and well, this is very hard to calculate. So what about if we basically only use this one? So we will make this function. So G2KZ will be divided by this theta function. We will left with is still not pretty, but it's nicer at least, right? Something like this. So yeah, that's basically what we are trying to do. We define the normalized Eisenstein series as this, only the one. So basically this form 2 times theta 2K is constant, right? So this is not really important. Since it's constant and this is a modular form, then this should be modular too. So here we define the normalized Eisenstein series as A to K is equal to 1 minus B for K for B to K, and the sum of all positive integer sigma to K minus 1 and times Bn. If we use K equal 2, we have this, K equal 3, we have this, we can calculate it. It's not very hard. So here we have the first 6 Eisenstein series, and this is actually pretty nice, except for E12. E4, E6, E8, E10, and E14 is quite special. What makes them special? So exercise 8 is easy, just expanding the font. So let's just calculation. And this is a special platform. So we define delta Z is a cups form with weight 12. Why? Because as you know, E4 is modular weight 4, right? And we have before this, we already have the properties that if F1 and F2 modular function, then the product is also modular function, but with weight K1 plus K2. So basically, if we multiply E4 3 times, right? E4 to the power of 3, we will get a modular function with weight 5. So E4 with weight 5. And with the same logic, E6 square is also a modular function with weight 12. And since these two here is in the form of 1 plus something, and this is also 1 plus something, when we subtract them, so 1 minus 1 will disappear, which means that this form will have 0 as the coefficient of q the power of 0, which as we have known and as we have defined before, this means this is a special case of modular form, which we call cusp form. So that's why this is a 12 cusp form, a modular form with weight 12 with an equal to 0, e0 equal to 0. Okay, now exercise 9 is also just more calculating. Okay, so we have a very useful formula here. It is called valence formula. So before we go to here, we define this first. So let F be a meromorphic on H, not identically 0, and let P be a point in H. Then the order of F at P is denoted by FPF is defined as the integer n such that F per Z minus Pn is holomorphic and non-zero at P. So the valence formula says that if F is a non-zero modular function of weight K for gamma, then F infinity plus half of F P1 plus 1/3 of P omega plus the sum of all this is equal to K per 12. And the important thing to note here is the fact that f t f here is always integer because it's the order. Order is always integer. So this is the important part. Okay. The proof of valence formula is quite long and pretty complicated, so I will not explain it here because we have limited time. But basically, you can read it in the slide here. So, using this valence formula, we can actually prove this corollary. So, first, the only modular form of big zero for gamma are constant functions. Why? So let f is a modular function with weight 0 and c be a value taken by fz. If fz is holomorphic but not a constant, then at least one value of fp will be positive, right? So using the following formula, if it is not constant, then this will have value. And all of this is also figured at least zeros. If we want the weight to be 0, then this is 0. This will create a contradiction because we have something that is at least 0 plus something that is more than 0 is equal to 0, which is a contradiction. This is why we can have it. Then corollary A, let k be an even integer. If k is negative or k is equal to 2, then the only modular form of weight negative n2 is the zero function. Why? Because once again, we use the valence. So if k is negative, it's pretty obvious. If all of this is the order is always at least 0. But if k is negative, then k per 12 is also negative, which is a contradiction. How come the sum of something that is at least 0 become something that is less than 0? So since there are no non-zero modular function of the negative, this means that the only modular function we have is 0. And what about 2? Why is 2 also only have 0? This is a little bit more not obvious, but basically, if k is equal to 2, then this I simplify. omega something is equal to 2 per 12 is 1 per 6. Okay. That as we know, all of this must be integer, which is integer, which is fp is always integer and non-negative. So, do we have any integer which satisfies this plus this plus this plus this is equal to 1 per 6, right? So basically, to make it a little bit more clear, we can multiply both sides with 6 to have 6 times f infinity plus 3 times f e plus 2 times f omega plus 6 times sigma f p is equal to 1. If all of this is integer, there is no such thing, right? So if we have this is 1 or more, then this is more than 6, already more than 1. Contradiction, which means this must be 0. If this is more than 1, it's already 3. 3 is already more than 1, which is a contradiction, which means this must be 0. If this is more than 0, this is at least 2, more than 1, contradiction. This must be 0, and with the same logic, this must be 0. But 0 plus 0 plus 0 plus 0 is not equal to 1, which is another contradiction, which means there is no such non-zero modular function. So, for k equal to 2, the only modular function we have is the 0 function. Quite interesting. So, Valence formula can be used to prove modular function with weight 0 and 0 is limited. Negative and 2 is also limited. Okay. So now, what about corollary 9? So, modular function with weight k is one-dimensional and is generated by Eisenstein k when k is 4, 6, 8, 10, and 14. Or in essence, all modular function with weights 4, 6, 8, 10, and 14 is the only way to have this kind of modular function is this. The Eisenstein series of sigma. That's why I say that this Eisenstein series is very special. Because this is the only modular function of its respective weight. Yeah, so modular function with k is always something like this. Maybe we multiply it with some constant, but it's quite trivial. This is quite powerful, right? We can guarantee that if a modular function has weight 4, it must be in the form of this times some constant. Why? Again, we will use valence formula. So let's try to prove it. First, valence formula. So some of you might have noticed that 12 is stick here. That's true. So unlike for 6, 8, 10, and 14, uh, modular form with vectors is actually more complex because it is not one-dimensional. We will also show it in this group. So basically, so the idea is like this. So yes, we can simplify the balance theorem into something like this. So we multiply it by 6, maybe. So 6 times f b plus 3 times f b plus 2 times f omega plus 6 times f b equal to b plus 2, right? So let's see. When k is equal to 4, mean that uh, we want the sum to be 2. But how can this be for any f something? This is always for f something is always non-negative and integer. So 6 times something plus 3 times something plus 2 times something plus 6 times something, where all of this is integer, which is more than 0, which is at least 0. How can we do this so that the sum is 2? So how? Now, as we can see, the only way to do this is to have this as 0, 0, 1, and 0. So there is only one way to express this. Okay, which means that P infinity plus infinity P e and P omega and all the other Pt here. So only solution is 0, 0, 1, 0. This is the only solution. Right. Which means that this is only can be done with a for. And the same can be done for k equal to 6, for example. If you want this to be 3. So how do we do it? The only way this can happen if we use 0, 1, 0, 0. What if 8? What if it is 8? This is 4. And the only way to do this is if it is 0, 0, use 2, and use other 0. Now, how about if it is 10? Then is 5. For 5, we have the only way to make 5 is if this is 0, this is 1, this is 1, and this is 0. And then for 14, 1, if this is 7, the only way to do this if we have this is 1 and this is 0 and this is 0. All of this, when k is 4, 6, 8, 10, or 14, all have unique solution. So only one possible way to use to find this. So then what happened if we use k equal, like I asked before, why is 12 skipped? Is 12 different? Let's see. If k is equal to 12, then It means we want the 6 times something plus 3 times something plus 2 times something plus 6 times something is equal to 12. Is equal to 6, sorry. As you can see, this times the solution is not unique because we can have it like this. For example, 1, 0, 0, 0, 0, 2, 0, 0, 0, 0, 3, 0, 0, 0, 0, 1. So this is not unique anymore. Which is why they are not one-dimensional. What about if k is more than 14? So maybe what if k is 16? You can try to research this yourself, but it is also quite easy to see that for k is more than 14, it's never unique anymore. Okay, so this is why. Okay. So maybe some time to write this down or screenshot this. Okay, then. So we can see that the valence theorem is really quite powerful. Um, Now, corollary 10, and let k be an even integer. Now, if k is less than 12 or k is equal to 14, so basically when k is negative, k is 2, k is 4, 6, 8, 10, or 14. So basically the specific case that we have mentioned before, then the cast form is always 0. So remember the difference that cast form is a specific case of modular form. That is the modular form that have the first term, so the in a0 times e0, right? Cast form 1 is a0 to become 0. But as we know from the previous one, that well, for k is equal to negative and k is equal to 2, the modular form is always 0. So this is easy. So if the modular form is 0, the cup form is also 0, right? But for k is equal to 4, 6, 8, 10, and 14, we have known that the modular form is always in the form of some constant times Eisenstein k, right? Where k is 4, 6, 8, 10, or 14 something, which means they are in the form of t times 1 plus something. Which means that the first form, the which means that A0 is always C, right? So the only way this Cost form can be formed is when C is equal to 0. But if C is equal to 0, then we have 0 times series is always 0, which means the Cost form of this weight is always 0. Okay, then for the second properties, the Cost form with weight 12 is always uh, constant time the Cost form that we have defined before. So this one, yeah, here, this one here. This is the only Cost form of weight 12, where only this n it's multiple, then this is multiplied by something constant. Okay, and then when for weight for so if k is more than 14, right? So as I have mentioned before, so what about when k is more than 14? So what about if k is 16, 18, 20 or something? What about this one? So we can see that the cup form of weight k is always the same as the cup form of delta, right? So delta is weight 5, right? And always this is multiplied by some modular form with weight k minus 12. And if we multiply this, then it will become modular form with weight 12. And since this is a cup form, so the A0 is 0. If we multiply it by any modular form, the first coefficient will also still be 0. Because basically cup form is can be viewed as q times something. So basically this is the corollary to for the weight that is bigger than 14, we have this for the properties. For the proof, we can repeat this. So using this corollary, we can then prove this properties that for any j that is bigger than greater than or equal to 0, then the dimension of M2J of gamma is like this. So to make it a little bit simpler, we can prove this using induction. So, okay. Okay, so to make it easier, this is uh, this is how we will prove exercise 11. So sorry if I didn't write it down because it will take a lot of time. So basically, how can we prove this? So we will use induction. So as we have known before, uh, right, for k is equal to 0, is only constant. For k is negative or k is 2, the only modular form that exists is zero function. And for modular function with k is 4, 6, 8, 10, or 14, they are all one-dimensional. So from this, we have that this is 1, right? Because zero function is still one, it still have a dimension. Sorry. When m0, we have known that it is constant. If it is constant, then the dimension is 1. While for m2, you know that modular form that Bejo is always 0 function, which means that the dimension is 0. And for g equal to 2, 3, 4, and 5, we have m4, m6, m8, all one-dimensional, right? We have known that it is 1 again, 1, 1, 1. J is 5 and J7 is also one-dimensional, right? The one that is not 1 is when J is equal 6, because as we have talked about before, when the weight is 12, it is not unique anymore, it is not one-dimensional, and you can check that it is actually two-dimensional. Yeah. The modular form of weight 12 is a combination of this. Combination of Eisenstein 4 to the power of 3 and Eisenstein 6 to the power of 2. So this is why M12 is two-dimensional. And we can just use induction. The first 8 term is correct using induction. We always satisfy this condition. But then how about when J is more than 7? So when J is more than 7, then we will use this property. Yeah. Use this two property. Yeah. And J is 8, that the first one is like yeah, we can prove it. Yeah. The dimension of MPJ is equal to the dimension of stj plus dimension of constant time atj. If constant time some answer time is always 1, this one, because of this, we have equal to this. This is because this is an induction, so this will be, we can just use the properties of it. Mm, we can finish the induction. It's not very hard. Yeah. Okay. So that's how to put the exercise 11. And this is theorem 11. So for any modular form with weight k, f can always be written in the form of this. So yeah, the sum of, so basically the combination of e4 to the power of e times e6 to the power of j, where obviously because we want this to be weight k, right? So this is weight 4 times e and this is 6 times j. If we multiply it, it means we have to make it k. So that's why this is the sum of all ej, where 4 times e plus 6 times j is equal to k. So basically there, this modular function with k is always a combination of e4 and e6 basically. We can prove this by induction. So obviously we know that e4, e6 is one-dimensional, where for AX, you can prove that AX is some constant times e4 squared. This is not hard because we already know the expansion, right? The expansion of A4 and A8. And so this is just a matter of confirming the coefficient. So you can prove that this is just constant time this square. Not really that hard. Just calculating it is ugly. So on until A14. Until A14. So yeah, this is the one-dimensional one, right? 10 and A14. As you can see, A12 is skipped because this is not one-dimensional. But you can see that A12 will be generated by this one, A4 to the power of 3 and A6 to the power of 2. You can show that A12 is basically something times this plus some constant time this. If we already have it until weight 14, for weight 16, 18, 12, and so on. It's just a matter of induction. It should be that hard. Okay. So this is just so this is some example. So what is the use of this Eisenstein series? It seems very uh, absurd. Right? What is the usage of this? So we can use this Eisenstein series to prove that this is equal equation holds. So the sum of all divisor of n to the power of 7 is actually equal to the sum of all divisor of n to the power of 3 times this. How? The fact that we use the fact that P8 Eisenstein series with weight 8 is equal to the square of Eisenstein series with weight 2. So since we already know, right, that this is how it is, then we can match its coefficient. So this is why we can have the equation that is connecting sigma 7 and sigma 3. And this is not the only one, because as we can see, right, modular form with weight k is always a combination of A4 and A6. So we can, if you are powerful enough to calculate it, we can always find the connection of sigma, which is sigma for some value that is big, can be connected to sigma 3 and sigma 5. So, yeah. Yeah, so this is the proof, right? Like what I said before, we know this is the expansion of AX, this is the expansion of P4. This is just a matter of matching the addition. So exercise 12 is also not very hard. This is again just trying to match the coefficient. You can show that Eisenstein series with 10 is the product of E4 and E6, while E14 is the product of A A6 and A4, and also A4 and A10. This one is trivial if you already prove this. This is trivial because, well, then we already know that AX is A4 squared, right? So, well, A10 is, according to this is A4 times A6. So, basically, you just need to prove that A4 is equal to this. Using these two connections, we can find the divisor sum of identities for sigma 9 and sigma 13. Again, we will use A4 and A6. This means we will be able to make it into the form of sigma 3 and sigma 5. This is left as an exercise. So,